Hi everyone, I'm Gabriel Maicas, and I'm here to present our work on training medical image analysis systems by radiologists. And I'm here to present our work on behalf of the whole team, which is composed of Gabriel from the Queensland University of Technology, Jacinto Nascimento from the Instituto Técnico de Lisboa, and Reid and Gustavo Carneiro from the University of Adelaide. So the training of medical image analysis systems based on machine learning normally follows the same script, which consists of collecting and annotating a large data set, which is then split into training and testing. You use a training set to train your classifier, and then you evaluate its performance on the out test set. So the main issue here is that you require a large data sets, which might be available for some programs like mammogram analysis, for example, but it's not available for breast image analysis from MRI, which is the problem that we're trying to solve. So there's a trick that you can use a pre-trained model to, and then fine-tune it in your problem with a small data set, but still relatively large data sets are required. Plus, if you're working with 3D images, there are not many pre-trained models available. So it's likely that your classifier will still overfit after you train following the usual pipeline. In our work, we propose to meta-train a classifier to learn to solve tasks or classification problems where only small datasets are available. So this is achieved by presenting many tasks that the classifier or our model has to solve, such that when the model receives a new task that you want to solve, you can just adapt to it and it will solve it accurately. So some example of tasks, for example, might be distinguishing breasts that contain any malignant findings from a breast containing benign findings. So another example could be distinguishing breasts with malignant findings from breasts that are healthy. The main issue here is in the order you present the task to the model during the meta-training phase. And this is the analogy we try to make in the title. While, for example, radiologists use a curriculum learning that is based on first starting to solve tasks that are easier and then moving on to tasks that are more difficult. In our system, in our work, the system automatically selects the task based on its parts performance. In particular, we want to solve the breast screening problem from MRI, and that means that we want to define which breasts contain any malignant findings. Normally, this problem has been solved following the usual pipeline that consists on the detection of possible regions of interest or lesions, benign and malignant lesions. And then you classify those lesions into malignant or non-malignant to decide the diagnosis. However, here we follow the opposite pipeline that consists on performing the classification of the image to perform the diagnosis. And if there is a positive diagnosis, then you try to detect the malignant lesions. The main difference between these approaches is that in the first approach, you need strongly labeled datasets, which are expensive to acquire because you need to label each voxel of the lesion. However, in the second pipeline, doing the classification plus the detection, you can train the system with weak annotations, which means that you just have a label per image. And we believe this is very important because these are the datasets that we have available at hospital. So we believe this is the way to go from here. Our dataset consists of 117 scans, for which we will use 45 for training. And because our methodology runs breast-wise, that means that we have 90 images for training. And each breast is labeled as healthy or 0 if there is no findings. It will be labeled as 1 or benign if we only find benign findings, and it will be labeled as malignant if there is at least one malignant lesion. So using the images exclusively from the training set will be the task that you can see on the left side of the image by grouping them into the different groups or tasks that you can see there. So for example, we have the task of benign versus malignant. We will get all the images that have any lesion, and the task will consist on distinguishing breasts that are benign from the breasts that are malignant. If we have the breast screening task, which is the one at the bottom, we'll have the whole data set, and we will try to distinguish breasts that are malignant from breasts that do not have any malignant lesion. During the meta-training phase, what we will do at each iteration, the model will sample a set of tasks that it will have to solve at each iteration. Eventually, the model will learn to solve classification problems that has a small data set. Then we will move on to the training phase, where we will take the particular problem that we will want to solve, and we use the pre-trained model from the meta-training phase as the initialization for the training in the problem that we want to solve. Finally, we will run the inference, as we will do with any classifier, to obtain the probability of malignancy of a particular breast. The main issue during the meta-training phase is how we sample tasks. So for example, if we sample the tasks on the first phase randomly, it will call that random sampling. But we can do something better. We can, for example, sample each task one at each iteration, what we call all tasks. But even we can do something better than that and sample according to a curriculum learning strategy. That means that we will sample tasks according to the improvement of performance in that particular task in the previous iterations. This means that we will sample more frequently tasks that are less stable. If instead of sampling based on the improvement of performance, we will sample based on the performance of the model in that task, we will have kind of a similar setup to a multi-arm validate problem. Here we have an example of how the system will work. And so in the left-hand side, you can see what's the improvement of performance, because we're using a curriculum learning strategy. And you can see that the system samples more frequently tasks with a high variation that are less stable. Then the system gets those tasks and will adjust them at each iteration. Again, in another iteration, we'll look at the variation in the improvement of performance. We will take the task that we'll sample more frequently the tasks that have a higher variation, that are less stable, and again, we give it to the model. After many iterations, the meta-training will converge, and we will use that pre-trained model as the initialization for the task that we want to solve, that is the breast screening task. We train it as usual, and finally, we will run the inference with the test set. That's what we will do with any classifier. So, how do we evaluate this? I'll present results, both images, and then I'll go into quantitative results. So in the left-hand side, you can see a true positive diagnosis of an image because it contains a malignant lesion that is pointed by the arrow. On the right-hand side, you can see a true negative diagnosis because the lesion that is present is benign, which is considered negative in a breast screening problem. Again, on the left-hand side, a true positive diagnosis, that is the positive classification of an image containing a malignant lesion. And on the right-hand side, you can see a false negative, which is the negative classification of an image or volume that contains a malignant lesion. In terms of quantitative result, we will use the area under the curve, or AUC, in the breast screening task to compare our system with different baselines. In this slide, you can see different ways of training the same model. So the underlying model that we're using here is a 3D DenseNet that has been optimized to solve the breast screening task. We can see that the model achieves an AUC of 0.83. But if the same model, if instead of training it as usual, we use our approach and we meta-train it first, we can see that boost in performance, and it goes to an AUC of 0.90. We compare also against two different baselines. So the middle baseline corresponds to a multiple instance learning setup that holds the state-of-the-art for the same problem in mammography, and basically fine-tunes the DenseNet in the second row with a multiple instance learning loss, and it achieves an AUC of 0.85. Finally, we also consider a multitask setup where we train the model with all the tasks at the same time with a global loss, and then we just test it on the breast screening task. We also evaluate our model according to check the task to evaluate the task sampling. And in the first two rows, you have, it's the same model, just the difference is how many tasks we have selected at each iteration of the meta-training phase. We can see that if we sample the task randomly, we have a performance that is similar to the performance of the baseline. But if we use smarter ways to sample, for example, the curriculum learning strategy, that's when we get the boost in performance. Especially the curriculum learning strategy, which means that you're sampling more frequently tasks that are less stable, achieves a slightly better result than sampling according to a multi-arm band-plate setup. That means that you sample tasks according to their performance. Finally, the last row shows what happens if you don't use the breast screening task in the meta-training phase. That means that you only use the task that we first defined, but not the one that we're going to use in the testing phase. And we can see that our model remains competitive. Finally, in this work, we have proposed to meta-train a classifier before the training phase. And the goal of the meta-training is to teach the model to solve problems where only a small training set is available. And this is achieved by asking the model to solve many classification problems during the meta-training phase. And we've seen that the way or the order in which you present the task really affects the performance, and it was the curriculum learning setup which yielded the best results. Finally, we've shown that if we don't use the task of interest during the meta-training phase, we can still achieve performance and our model remains competitive. Finally, I'd like to acknowledge the Australian Research Council for the funding provided for this work, and I'd like to acknowledge also my collaborators and my supervisor, Gustavo, for his supervision during the PhD. Any questions? Thank you for your attention.
Are there any questions?